Okay, so let's get started. And before we actually start with the lecturing here, these are the student representatives.
Hi. We're thinking we're going to send around 2 pieces of paper where you can write your feedback. So one of them is about the lectures, exercises, and the quiz, which is on the lecture, the exercise. And the other one is about the project, ping pong, and logistics, and things like that. So I guess we'll send one from each direction. Okay.
And the idea is that we will discuss this on Thursday, and then see whether we can make what changes we can make. We still have some time to do that.
Yeah.
Okay.
So these will go up again on Thursday, if you can't think of anything.
Yeah. Yeah. So. Thanks, guys.
Yep.
Okay, so we're talking about efficiency of stop and wait, and what we did just before the break here was to draw a simple timing diagram of what's going on in the best case where we actually do a successful transmission of a frame at the first attempt. Okay, so we have a time axis here for the transmitter and the receiver, and the transmitter starts to send a frame here consisting of a number of bits. Let's call them NF. NF for the number of bits in the frame. So it will take some time to transmit that, and the time here depends on the data rate of the underlying communication scheme, right? So the time it takes for one frame to be transmitted depends on the number of bits divided by R, the data rate on the layer below us, right? So where R is the data rate in bit per second, and and NF is in bits. Okay, and the same thing happens here. The acknowledgement here consists of n ACK bits. Oops, sorry. So the time it takes to transmit one ACK, T-ACK, is the number of bits in the ACK, NA divided by R. The processing time here depends on, of course, on the hardware of the transmitter and receiver, and also the workload on that hardware at that time, the operating system. There could be other things that the hardware is busy doing. So basically it's a technology and then also a little bit on how things are implemented. So let's just assume that they happen to be the same in both ends, right? For no particular reason except for convenience. So the processing time here, we just think of that as something that depends on the speed of the hardware and what it's currently tasked to do. So we only have one thing left here, and that is then the propagation time. And here, propagation time could be like if this communication between the transmitter and receiver is over one physical medium, it's actually the propagation time over that medium, which is somewhat less than the speed of light, right? That's the speed of the propagation there, and depending on the medium, it's a little bit different. It could also be if there is multi-hop, there will be several of these propagation times and so forth. But for simplicity, let's assume that there's just one medium here. And then the the propagation time depends on the distance, D, which is between the transmitter and receiver. So D meters, and then divide through by this propagation speed. And the propagation speed, okay, let's assume that this is a fiber optical channel or something like that. Then the speed of light in a fiber is about 2/3 of the speed of light in vacuum. So let's take that as an example. So 2/3 times C0, where C0 is the speed of light in vacuum, which is 3 times 10 to the 8 meters per second, roughly. Okay, and then if we do some calculations here, we basically get this to be 5 times D nanoseconds. Okay, So if we have something which is 1 meter distance, it takes 5 nanoseconds to propagate. Okay, so this is a short distance. But if it's several kilometers, say it's 1 kilometer, then it's 5,000 nanoseconds or 5 microseconds. Okay. Typically, I mean, in the scale of things, these are almost negligible, depending on if it's only over one medium, except if it's over very, very long distances. So, for instance, satellite channels or interstellar probes or transatlantic fiber optic channels, then propagation time could be sizable, right? Agreed. But otherwise, it could also be small. Now, in the grander scheme here, then this communication between the transmitter and receiver is done over several physical medium with intermediate nodes in between them, and then the propagation delay could be sizable, could be significant. So if you do a ping, for instance, you're familiar with the command line program ping, it gets a ping to a server, and that's milliseconds for sure, it could be seconds even, right? And that is mainly the propagation time through the switches and all these things, right? Okay, so anyway, so we're now ready to say something here about data rates and so forth. Just to illustrate what we're trying to do here is that we are working in a layered structure where we have at the layer above us is here. Here we have some service data units that needs to be transmitted. So here we have at the TX, we would like to transmit some service data units to the receiver side here. Okay, so this is the virtual communication that's going on. The upper layer is using us to do this transmission, and we have this stop and wait transmitter logic that's communicating with the stop and wait logic at the receiver side. Okay. And then we are transmitting here, in our logical communication, we are transmitting information frames this way, which is the service data unit that we receive from above, plus sequence numbers, CRC bits, and so forth. So there will be some overhead bits here. So let's just write them as a header, and then there is possibly a trailer here also. But this header and trailer has some bits in it, right? Sequence numbers and all these things. So these are the things that we are transmitting from here to here, logically. But of course, this goes down to the layer below us for actual transmission, like this. So, and the layer below us might have other protocol overheads and so forth, but let's ignore that and just assume that here we have a physical connection that has a certain data rate, and that's what we call R. So this is the data rate of the layer below us. Okay. Okay, and then on the reverse link here from the receiver to the transmitter is these acknowledgement frames with headers and all these things. So this is what's going on logically. Of course, physically it goes in the layer below us. So what we would like to do now is to say we would like to use this resource, the bits per second we can get from the layer above us, as efficiently as possible to deliver a high-speed service to the layer above us. So these service data units goes between the transmitter and the receiver in the layer above us with some data rate that we call the effective data rate. Okay. Physically, these goes down like this and goes up like this, right? But from a user on this layer, it seems like we're transmitting these data units, and it takes some time for them to arrive at the receiver, and the time it takes for one bit to be delivered, or this is the effective data rate essentially. Okay, so if you take the number of bits in the SDU and divide through the time it takes to deliver it, That gives us the effective data rate. This effective data rate, of course, depends on the data rate of the layer below us, right? But it also depends on how efficiently we are running our protocol. Okay. So what we want to do now is to calculate this number, the effective data rate, given the data rate below us, and with some assumptions on these parameters, right? Or with these parameters. So we want to have an expression for the effective data rate in these time variables. Okay. So the effective data rate, RF, and I put in a 0 here also, and the reason for this is that now we're going to calculate the effective data rate when there are 0 errors, meaning that there are no errors on the layer below us. And then in a while, we will compute also the same thing, what happens when we start to get errors here. Right? But so this is the best we can hope for when transmission is error-free. So what is the effective data rate? Well, it's the number of bits in the service data unit divided by the time it takes to deliver it. So what is the number of bits in the service data unit? Well, we know that the whole frame here has NF bits in it. That's what we said earlier. The whole frame which is transmitted at the lower layer has NF bits in it. So the number of bits in the service data unit will be less than NF. So it will be NF minus NO, O for overhead bits. And then we divide through by the time it takes to deliver the frame. So how long does it take to deliver the frame? Well, let's go here and see that we started to transmit the frame at this point in time, and it was completed at this point in time, in the sense that this is the first time we can start to transmit the next frame, right? It was actually completed already down here, but the transmitter did not know this until this time. So the transmitter could not start to transmit the next frame until the first frame has been delivered. Okay? So it's actually like this. Okay? So these overhead bits is a sequence number, the CRC bits, all these things that needs to be in the frame that we transmit. Okay. So then it's now we're ready. So now it's just to calculate this, right? So it's a little bit of algebra coming now. Okay. So this is the effective data rate. So this is important in itself. If we want to say something about the efficiency of this layer, we'd simply take the effective data rate and divide through by R. So this is how efficient we are. This will always be a number which is less than 1, right? We cannot possibly communicate any faster than R bits, but we can certainly communicate slower. So the efficiency eta 0 is RF 0 divided by R. Okay, so let's calculate that. So this is just NF minus NO divided by T0 times 1 over R. So let's take T0 and multiply that with R. So T0, what is that? Well, it's 2 times T prop plus T pros plus TF plus T ac. Right. So I just, okay. Okay, so it should be 1. No, that's it. So I just substituted in the value for T0, being twice T-pros plus T-prop plus TF plus T-ac. TF, we know that that is NF divided by R. So R times TF is just NF. And R times TAC is just NA. So we're multiplying in R into the lower parentheses here. We get this to be NF minus N0, NO I mean, 2 times R T pros plus T prop plus R times TF, which is NF, R times TAC, which is NAC. I'm just plugging in expressions here. Okay. So now what we want to do here to clean up this expression a little bit is that we divide the numerator and denominator with NF. Okay. So just continue here. And then if we divide the numerator with NF, we get 1 minus NO divided by NF. And in the denominator, we get 1 plus NAC divided by NF plus this other expression, which is 2 T prop plus T pros divided by R times NF. No, sorry, it should be R here and R NF, like this. Okay, like this. Okay, I'll lift this up. So we see here we can cancel the R's here. And then we have the final expression. So let's interpret this. So this is the efficiency. We would like the efficiency to be high. It will be a number which is less than 1. Okay, so what makes this less than 1? Well, obviously this part here reduces the denominator, so it's a harmful thing. Okay, so what is this? This is loss due to protocol overhead. Okay, because it's the number of overhead bits divided by the number of bits in the frame. Okay, so of course, if we have a fixed number of overhead bits, we would like to make the data frame large to make this loss negligible. Okay, so it's good to have long frames. At least the ratio between the overhead bits and the data bits, the total number of bits, should be a small number. Okay, and then what makes the denominator non-ideal? Well, it's the addition of these two terms, which will lower the efficiency. And the first one here is the overhead due to the acknowledgements. Okay. So this is the loss due to ACKs. And then we have this quantity left, which, if I clean it up, is 2 times T prop plus T pros divided by NF. There's something wrong here. This R should still be here. Okay. Sorry for that. Okay. I don't know why I messed this up, but here's the correct one at least. Okay. So this is loss due to something called the delay bandwidth product. Okay. So this delay bandwidth product will pop up. We will see that returning in other settings as well. So what it is that the delay bandwidth product is the product of a delay and the bandwidth, okay, in its most general sense. So, and bandwidth in this setting means data rate. So we have the data rate multiplied with some delay, okay, so that's a delay bandwidth product. And then it's then normalized with the number of bits in the frame. So if this is large, then we will have low efficiency. Okay. So let's make an example and see what type of efficiencies we can expect. So suppose the data rate is 1 megabit per second. Okay, so we have some physical layer here. It can handle 1 megabit per second. Okay, and we are transmitting frames of 1250 bytes. So that's a typical. It's almost like an IP packet or something like that. So it's 1250 times 8, which is 10 to the 4, 10,000 bits. Okay. So this means that the time it takes to transmit the frame is then 10 to the 4 divided by 10 to the 6, right? So we have 10,000 bits on a 1 megabit per second line, so this is 10 milliseconds. Okay. And then suppose that the ACK frame here is shorter, say it's 200 bits or something like that. So it's 200 bits. Then the time it takes to transmit an acknowledgement is quite short. It's 0.2 milliseconds. Okay. So these are the basic facts. And now, suppose we have a little bit variable delays here. So, and the delay is that 2 times tprop plus tpros. Let's assume that these could be in milliseconds. Say 1, 10, 100, or 1,000 milliseconds. Okay, just to show how things change when we have different delays. Then T0, the reaction time. So what is T0? Well, it's the 2 times tprop tpros, which we had here, plus the frame time plus the acknowledgement time. It will be then here 1 milliseconds plus 10 plus 0.2 milliseconds. So it will be 11.2 milliseconds at this point. And it will be 20.2 milliseconds if we have this delay, and then 110.2 milliseconds if we have 100 milliseconds delay, and so forth, right? So 110 times 2 milliseconds like this. Okay. Right, okay. So the reaction time D0 here is this number plus this number plus this number. Okay, so when we vary the delay here but keep the frame sizes fixed, these are the numbers we get. Okay. Now, so let's calculate then the effective data rate that we get here, which is just taking the efficiency here and then multiply with 1 megabit per second. Then we get the effective data rate here. So you just have to trust me on this one. I would just write down the numbers here. So if the delay is 1 millisecond over the channel, then we get a data rate which is 0.875 megabits per second. Although the physical layer below us was able to produce 1 megabit per second, which means that the efficiency we get is exactly 87.5%. Okay. Right, so that's what we had. Now, if we increase, if the delay is 10 times higher, 10 milliseconds, what happens then? Well, we just go through the motions, and here then we actually get 0.485 megabits per second. Just putting in the numbers. So here we see we only get half the data rate which was available, right? So the efficiency here is less than 50%. And if the delays increases even further, it gets even worse. So for 100 millisecond delay, we get 0.089 megabits per second. And for 1,000 milliseconds delay, it's 0.0097 megabits per second. And these are also the efficiency numbers, so just another interpretation of this. So here we see something which is disturbing, right? That if we are transmitting IP packets over a physical layer where the delay starts to become significant, we see that the effective data rate goes from, at least close to 1 megabit per second down to this horrible number, right? This is only like what, 9.7 kilobits per second. We have 1 megabit and we deliver 10 kilobits up. Not very good. So suppose the layer above us complains and wants to have a higher data rate. What can we do? Well, one thing is to blame somebody else, namely the layer below us, and exchange that 1 megabit per second to 1 gigabit per second. That should do it, right? Okay. So let's try that. And let's calculate the effective data rate for this case. Just filling out the here. Let's write it here. So the effective data rate here when R is 1 gigabit per second. I mean, I spent a lot of money here, bought this fancy physical layer that's 1,000 times faster than I had before. Surely this would be better, right? Okay, so for low delays, it seems pretty good. We get 9.7, but what? 9.7 megabits per second. Okay, I had a gigabit down, I delivered but 10 megabits up. It's not really good. And it gets even worse if we go to the right here. Here's 0.98 megabits per second. Here's 0.098 megabits per second. And here's 0.0098. That didn't work, right? It did not work. So when we have problems with high delays, it really doesn't matter how fast the layer below us is. We can buy something which is 1,000 times faster, and what did we gain? We gain from 0.0097 to 0.0098, right? So something is bad here. Okay, and let's see if we can understand why this is the case. And the answer is actually here. That we see that by increasing the data rate, which of these timing variables is affected by that? So if we increase data rate, increase R, are we going to change the propagation time? No. Are we going to change the TF, frame time? Yes, right? Because this is the number of bits per frame divided by R. So we can make this arbitrarily small, right? But the processing time remains the same. The acknowledgement time, we can shrink that to almost nothing also by increasing R. But the propagation time and the t-pros remains the same. So when increasing the data rate only means that we shrink these parts to almost like solid lines, if you like. But the overall data rate is then dominated by the propagation delays and the processing delays. Another way to say this is that if we look from the transmitter's point of view, when are we using the physical layer? We are using the physical layer during this time, right? And here, it's not used. This is all idle time. Question?
What's the processing time have nothing to do with the packet size?
Well, okay, it scales a little bit with it, but in general, it's not so affected by it. Yeah. So I'll take that back. We say that the frame size is the same, so the number of bits here remains the same, which then makes it reasonable that the processing time is the same.
Okay.
Right, you have the same number of bits to process, right?
Okay.
Yeah. The transmission time scales with the bit rate on the physical layer below it, right? So the problem is here that from the transmitter point of view, we're idle. We're not using the physical layer for most of the time. Okay. So that's the main problem. So what to do about that? Well, let's use it all the time then. So keep on transmitting frames, even though we have not received acknowledgements of the frames that we did earlier. So we will see that later on, that this is what's done if we have problems with large delays, or in general with large time bandwidth products. Okay. So, going back to this now, so now we have calculated here the effective rate and the effective efficiency under the assumption that the physical layer below us is perfect, no errors. So what happens if there are also errors here? Well, things will become worse, obviously, right? But how worse? How much worse? So let's calculate this. And the key thing the key parameter here is the number of transmissions we need to do in order to deliver a frame. So here's one transmission of the frame. Now suppose that this was not decoded correctly, so this disappeared somehow. Either that the acknowledgement disappeared or this one disappeared. Then what's going to happen is that after the timeout, the transmitter will try to transmit this once more. So that will happen at the earliest here, but maybe at some later time, depending on what the timeout value was set to. And then we would redo the process, and then there is still a probability that the frame will be lost, and then we have to do 2 more transmissions, etc., right? So we can define a variable called NT, which is the number of transmissions needed for completion of one frame, and that's going to be a random variable that depends on the probability of error over the channel. So okay, so let NT be the number of transmissions needed in order to transmit one frame. Okay, this is going to be a random variable. because errors will occur randomly on the channel. Suppose frame errors occur independent of each other with probability PF. Okay. So PF is the probability of a frame error, so a number less than 1. Then the probability that NT, the number of transmissions, is equal to some number I, we can express that in terms of PF. Okay, so how are we gonna do this? Well, we see that each time we try, we have a probability of PF of a failure. Okay, if we want to calculate the probability of that NT is equal to I, this means that we have tried I minus 1 times and failed at all those times, and the last time we were successful. Okay, so we have first of all the failure for the first frame, the probability of that, and then the probability for the failure of the second frame, that's PF, and then the failure of the third frame, etc. We get I minus those factors, and then the last frame we got lucky and it went through, and that happens with probability 1 minus PF. Okay. So here it is, the probability that we need exactly I times to transmit the frame. It happens with this probability. So this is then PF to the power I minus 1 times 1 minus PF. Like this. Okay, so on the average, how many transmissions do we need? Well, let's take the expected value of NT. That's the average number of tries we need to do. So here we had the probability mass function. So let's just calculate this. It's a sum over all possible values of NT, and the smallest it can be is just 1. So that means that we got lucky right away. Okay. The worst it can be is infinity. We can be maximally unlucky for the rest of the universe lifetime. So it's a sum from I equals 1 to infinity of the probability of I, okay, the number of transmissions we're considering, times the probability that NT is equal to I, which is this one. So P to, oops. I times P to I minus 1 times 1 minus PF, like this. Okay, so this is the expected value, the expected number of transmissions we need to do. All right, so here we see this seems to be one of these sums that we find in our math table. And indeed we do. So I'm not going to bore you with the derivation of this. Or you could just trust me on that. If one goes through this, one sees that this evaluates 1 minus 1, 1 over 1 minus 1 over 1 minus PF. Okay. Sanity check. If the probability for failure is 0, we need 1 transmission. If the probability for failure is very large, close to 1, we need many transmissions. So at least it scales in the right direction. Right? Okay, for no reason which is obvious at this point, we would like to look at the random variable NT minus 1. So these are the number of retransmissions we do before we get the successful transmission. And then that is simply 1 over 1 minus pf minus 1, which we can write as pf divided by 1 minus pf. We will need this equation a little bit later. Okay, so now we know something about the average number of transmissions we need to do. So now let's figure out what is the average time it takes to deliver a frame. Well, we see here that the shortest time it takes to deliver a frame is equal to t0, right? That's the best we can hope for. And with what probability does this happen? Well, it happens with some probability that we can enter into this one. Now, the next frame will be started to be transmitted after the first transmission has timed out. Okay? And then there's the second try and the third try and so forth. Right? So the time it takes to complete a transmission, T with subscript SW for stop and wait, it will be the total number of transmissions we have done minus 1. So these are the number of retransmissions we have done times the time between such transmissions, which is the timeout value. Okay, the time, remember that we start a timer when we transmit the frame. After t out seconds, we say, okay, the frame is lost, and then we retransmit. So for each retransmission, we need to do this. And in the last transmission, which is successful, it takes t0 seconds to do this. Right? And t0 is this time. Okay. Are we okay with this? Okay, so we need to transmit the number of times, nt times. It's a random variable. Nt minus 1 of those are retransmissions, unsuccessful retransmissions, and they will be spaced by t out, which is longer than t0, and the last one will take t0 seconds. So the expected time it takes is just the expected value of the what we have up here, which is the expected value of nt minus 1 times t out plus t0. This is what's random, right? We don't know how many transmissions we will need. It would depend. Right? Okay, and this thing, the expected of nt minus 1, the expected value here, we know what that is. It's this. It's pf divided by 1 minus pf. So we can simply write this as pf time out divided by 1 minus pf plus t0. Okay, so what is the best timeout value we can put? What would you select the timeout value to if you knew t0? Zero? The timeout to be 0. That means that when we start to transmit the frame, we deem it to be lost and retransmit the frame again, retransmit the frame again, retransmit the frame again. That's not good. So we need at least to give the frame the chance to complete before we start a retransmission, right? So the timeout needs to be larger than t0. Otherwise, we will probably Otherwise, we will do extra retransmissions, even though that this might be successful. So we want to pick the timeout to be larger than t0. How much larger?
As little as possible.
Yeah, exactly. So 1 microsecond larger or something like this. So let's put it equal to t0. Okay. So for t out equals t0, this also simplifies somewhat. So then we simply get pf 1 minus pf plus 1 times t0. And this is t0 divided by 1 minus pf. Okay, so this is the average time it takes to transmit one frame with stop and wait if we have a frame error probability of pf in the layer below us. Okay, so if the frame error rate is 0, then it takes t0 seconds to transmit. If the frame error rate is larger, then we need more retransmissions. Okay, so it seems to be correct on the surface here, at least. So to summarize, the effective rate we get for stop and wait, it is the number of bits, information bits in the frame, which is nf minus n0, and then divided by the expected value it takes to deliver that frame. So the expected value of TSW. The expected value of TSW we have calculated here. So this is 1 minus PF times NF minus N0 divided by T0. Just plugging in the numbers. And what we have here is the effective rate when we had 0 errors. So this we called RF0. So we see that the effective data rate is the effective data rate when we have no errors multiplied with this number, 1 minus PF. So when PF is 0, we indeed get the data rate that we get with 0 errors. If PF is increasing, we see that we get less and less. So this is the impact of errors. Okay, and if we look at the efficiency, we can go through the same calculations, and then we get it to be 1 minus PF times the efficiency with 0 errors. So actually, the end equations are quite simple, almost intuitive, that the degradation we get in data rate or in efficiency is linearly proportional to the error rate we have on the channel below it. But now we also proven it rigorously. Okay, so if I just get 30 seconds now, I'm sorry for taking this time, but the end result, the take-home message now is that stop and wait is inefficient when we have large delays or when we have lots of errors. For large delay bandwidth products, or large PF. Okay, that's it for today.
Across the tool.